Good morning everyone. So today we are going to cover the last topic of Bessel functions, which talks about the orthogonality of Bessel function. So we have discussed the orthogonality of legendary polynomials. Similarly, we can introduce the orthogonality of Bessel function, which says that if lambda m and lambda n are positive zeros of jpx, then the integration from 0 to 1. In case of legendary polynomial, it was -1 to 1. Now it is 0 to 1. And then x is there, which was not there in legendary polynomial. So 0 to 1 x jp lambda mx jp lambda nx dx is 0 if m is not equal to n, and is 1 by 2 jp plus 1 square lambda n, where m is equal to n. We are not going to cover the proof of orthogonality, but using orthogonality we can easily introduce the Bessel series in the same way we introduce the legendary series. So we say that let fx be a function defined from 0 to 1, then fx can be written as a linear combination of Bessel functions, that is summation an jp lambda nx. And now an can easily be computed using orthogonality, because if you multiply both the sides with x and integrate from 0 to 1, then on the right hand side there would be only one term if we take n or m to be fixed. So there would be only one term which is non-zero because of orthogonality, and all other term would be equal to 0. So let's multiply both the side with x, jp lambda mx. So left hand side becomes integration 0 to 1 fx dot x dot jp lambda mx dx, and in the right hand side, because of the summation there are infinitely many terms, but you can see that when lambda m, so these are the two terms which gives you non-zero term, and all other terms gives you 0. That's why the right hand side would become am by 2 jp plus 1 square lambda m. And if you take the other terms on the other side, then your am can be easily computed. So this is your am. Yes, there is a generalization, so please do remember the formula. There is a generalization for orthogonality also. If you consider the interval from 0 to a instead of 0 to 1, then there would be few changes which you can easily observe, and similarly there would be changes in the Bessel series also. Okay, now let's try some interesting question. So the first one says that let fx be defined as follows. Then you need to show that fx can be written as a linear combination of Bessel function j naught lambda nx, which means that you simply need to show that when you write the Bessel series for fx in terms of j naught lambda nx, then your an would be j1 lambda n by 2 divided by lambda n j1 square lambda n, j1 square of lambda n. Yes, so fx you should write it as summation an j naught lambda nx and use the formula for an and see what you are getting. Please do try to solve it by yourself. So if I use the formula from the Bessel series an, then it is 2 by, there it was jp plus 1, p is 0, that's why it is 2 by j1 square lambda n, then 0 to 1 x fx j naught lambda nx dx. Now fx is given to be 1 from 0 to half and otherwise 0. So that's why I took the interval 0 to half, then fx is 1 and j naught lambda nx dx. Now I have this integration of x j naught lambda nx, and outside I have 2 by j1 square, and what I need as an, I need it in the form of j1 lambda n by 2. j1 square is already covered, but j1 is not there. So I want that this integration j0 and want to see that does it can be transformed into j1. So I have to use the recurrence relation. Now try to identify which is the most suitable recurrence relation. So there is a recurrence relation which says that, so we know that d by dx of x raised to the power p jp is x raised to the power p jp minus 1. So if you put p is equal to 1, then d by dx of x j1 is x j naught, and if I take integration on both the sides, then it becomes x j naught is x j1. Yes, so now I have the integration x j naught lambda nx, so there is a constant multiplied by x. That's why when you take the integration of x j naught lambda nx dx, it would give you x j1 and 0 to half and divided by lambda n. Yes, because x lambda n was there. Now you simply substitute the values. So you had 2 by j1 square lambda n, then 1 by lambda n can be taken outside, and x j1 lambda nx and 0 to half. When you substitute 0, this interval will be 0. So when you substitute half, then you will get 2 by lambda n j1 square lambda n, and then 1 by 2 j1 lambda n by 2. So this is what you are looking for. So this is j1 lambda n by 2 divided by lambda n j1 square lambda n. And if you substitute the value of an, then you will get the required series which we are looking for. Yes. Let's try one more question which says that let fx be a non-trivial solution of this equation such that y of x is bounded near x is equal to 0 and y of 1 is given. We need to find the value of 0 to 1 x y square pi of x dx. Now first thing is that since we are discussing the Bessel functions and Bessel equations, it means that first we need to see is the given equation is Bessel equation in some form, can it be transformed to Bessel equation. So given equation can be written as x square y double dash plus x y dash plus x square minus 1 by 4, so x square minus p square, y is equal to 0. It means p is equal to half, and it means that your y of x is c1 j half x plus c2 j minus half x. Now we have given some information. Y of x is a non-trivial solution, which is this, and it is bounded near x is equal to 0. So recall that we have discussed that jpx is bounded near x is equal to 0 while j minus px is not bounded near x is equal to 0. So y of x is bounded near x is equal to 0. This implies y of x, or this implies j minus half x is 0, or you can simply say that this implies that the bounded solution is y of x is equal to c1 j half x. Now next information is y of 1 is equal to root 2, and I know that we have computed in the last class that j half x is root 2 by pi x and sine x. So y of 1 is equal to root 2 implies root 2 c1 and 2 by pi. So I substitute x is equal to 1 and sine 1. Yes, so that gives me c1 is equal to root pi by sine 1. Root 2 cancels out. It means my y of x is root pi by sine 1 and j half x. Now I want to find the integration of x y square pi x dx. So x and y square means pi by sine square 1 and j half square pi of x dx. So we already know j half x. So in j half x we replace x by pi x. That gives you the value of j half square pi x. So this would be equal to pi by sine square 1 is a constant, 0 to 1, and then 2. So root 2 by pi x is there, so root 2 is, so square is there, so 2 by pi and x got replaced by pi x and sine square pi x dx. Yes, now pi would cancel out, and if I solve it further, then it simply becomes 1 by pi sine square 1, 0 to 1, and this x would also cancel out, and sine square x can be written as 1 minus cos 2 pi x dx. So if you simplify it further, then it is 1 by pi sine square 1 x minus sine 2 pi x by 2 pi, and that gives you pi sine square 1. So that is the required answer. So that's all from this chapter. In the next video we will cover Laplace transform. Thank you.